In this example, we're going to calculate the difference between the molar enthalpy of two polymorphs of calcium carbonate versus the internal energy of that same compound. Okay, so the question tells us that the change in molar energy as calcite converts to its polymorph aragonite is positive 210 joules per mole. So right off the bat, we can say that the change in internal energy is 210 joules per mole. Calculate the difference between the molar enthalpy and internal energy changes when the pressure is 1.0 bar, or 100,000 pascals. And it gives us the mass densities for the two polymorphs of the substance. We have the internal energy. What we need to find is the enthalpy of the reaction. And we find the enthalpy of the reaction by subtracting the enthalpy of the product by taking the enthalpy of the product and subtracting the enthalpy of the reactant. So if we're changing from calcite into aragonite, that means that we want the delta H of the aragonite, we'll mark as an A, minus the enthalpy of the calcite. Okay, our general equation is change in enthalpy is equal to the change in internal energy plus pressure times volume. So we can substitute that for both aragonite and calcite. Equals delta U plus pressure times the volume of the aragonite minus, I'll put some brackets around these at first anyways, delta U plus pressure times volume of the calcite. Already we can simplify this because we know that the delta U is the same for both. And what we're really looking for is the difference between the enthalpy and the internal energy, so we can move that to the other side of the equation. And what we're left with is the pressure times the change in volume from the aragonite and the volume of the calcite. Okay, so it doesn't give us the volume, or the molar volume in this case, of either of those compounds. What it does give us is the mass density. So how is that going to get us volume? Well, density, or rho, is given in grams per centimeters cubed. And we said in our last video that we can use the molar mass to find this. So the molar mass of this substance is 100.09 grams per mole. So now on the page we have units of moles and volume. And what we want is the amount of volume per mole. So the molar volume is going to be the molar weight divided by the density. And we can sub that into our equation. Pressure, molar mass, and now we have the density of the aragonite, which is 2.93 grams per cubic centimeter, minus 1 over the density of the calcite, 2.71 grams per centimeter. And we can insert our values, so 100,000 pascals times 100.09 times negative 2.77 times 10 to the negative 2. Oops, I lost the screen there, but it's times 10 to the negative 2. And that equals negative 2.8 times 10 to the negative 5 Pascal cubic centimeters per mole, or negative 0.28 Pascal meters cubed per mole, which is equal to negative 0.28 joules per mole. And that's our final answer. So 0.28 joules per mole is not a large amount of energy. Even in this case, we can see that 0.28 joules per mole is about 0.1%. of the internal energy. So for solids changing phase or changing state, the difference between internal energy and enthalpy is like this. It's usually pretty negligible. Okay, let's move on to our next example. Okay, in this example, we're looking at the combustion reaction for hydrogen with oxygen, producing liquid water at 298 Kelvin. And unlike in the last example, where it was only dealing with solids, now we're changing the number of moles between the reactant and the product. We'll start by writing down the equation. Delta H equals delta U plus P delta V. And we're going to make a substitution based on the ideal gas law, that PV equals nRT. Or that change in volume is equal to a change in moles as long as pressure and temperature are kept constant. So let's substitute that in for delta U plus change in moles, RT. And the real change in volume here is the change in gas, in the moles of gas. So what we're really interested in is looking at the change in the moles of gas from the reactants to the products. On the reactant side, we have 3 moles of gas. And on the products, we've now lost all of the gas and produced a liquid. So we have 0 moles of gas. So if we're looking at the difference between the enthalpy and the internal energy in this reaction, we have the change of moles, which is going to be negative 3 moles of gas, times the gas law, constant, so 8.314 joules per mole Kelvin, times the temperature in Kelvin, so 298 Kelvin. And this works out to around negative 7.5 kilojoules per mole. Now you'll notice in the last one we were talking about a fraction of a joule per mole, and now we have 7.5 kilojoules, or 7,500 joules per mole. So a significantly larger difference when we're talking about gas versus solids and liquids. Which is why when we're dealing with solids and liquids, we can assume that enthalpy and internal energy are more or less the same. But when we start changing the number of gas moles between the products and the reactants, we have to calculate it out because the difference between the enthalpy and the internal energy will be significant based on the difference in the volume of the gas.